Okay, last class we learned our basic shapes, squares, circles, no, wrong basic shapes. We learned our basic electron group shapes. We learned two shapes, two electron groups up through 6 electron groups. So 2 electron groups was our linear geometry, absolutely straight line, 180 degrees bond angle. When we bump up to 3 electron groups, if they're all the same, we're going to have 120 degree bond angles, and it's going to be trigonal planar geometry. It's completely flat in the plane of a piece of paper or a board or a desk or any other thing that's flat. For 4 groups, we have tetrahedral geometry. Now we're branching out into 3 dimensions. Where is that? Here it is, tetrahedral geometry. And that's like if you make an X shape with your body and then turn 90 degrees at the torso. And this gets slightly more separation than the 90 degrees that's predicted if you just do the X shape. So we get 109.5 degrees, and this is tetrahedral geometry where we've got 4 faces if we made this into a die. Once we jump up to 5 electron groups, we've got our trigonal bipyramidal geometry. So we've got 5 groups, and this is where we venture into labeling things as axial, up and down, or equatorial in the around area. So up and down, and then equatorial is all around and to the sides. But like flat on a table is usually how we show it. And in trigonal bipyramidal geometry, we've got basically 2 pyramids with these 3 as the corners in the equatorial positions, and then each of the pyramids, the up and the down. Once we jump up to 6 electron groups, we are in octahedral geometry. We've got 4 equatorial groups with 90 degrees between them. We also have 90 degrees between our axial and equatorial positions. Those are the basic shapes. There are some more complicated shapes. Let's determine the molecular geometry of CCl4. To start, we need to be able to draw a Lewis structure for CCl4. We can go about this the long way. We've got a carbon, we've got chlorines, we've got 4 of them. Carbon is going to give us 4 valence electrons. Chlorine is going to give us 7 valence electrons each because of the column that they are in on the periodic table. So we'll do 4 times 20, or 4 times 7 plus 4, which gives us 32 valence electrons. The carbon is going to be in the middle because that gives us the most symmetry. And then we need to get everything connected. All the chlorines are going to bond to the carbon. That's 4 bonds with 2 electrons each, so we've used 8 electrons with bonding. That'll leave us with 24 remaining electrons. Remember that our goal is to get full octets. We want 8 electrons on each atom. And covalent bonds count because they're sharing. So chlorine currently has 2, this other chlorine has 2, the carbon in the middle has 4 bonds, and so it has 8. So we can add to our chlorines on the outside to get them up to this 8 count. We can add 6 to each, and since we've got 4 of them, 6 times 4, that will place the rest of our 24 remaining electrons. 4 times 6. Okay, so that's all of our electrons placed, and now we've got full octets as well. Then we can determine the molecular geometry of this compound by looking at our central atom. Carbon has 4 groups on it. 4 groups attached to the carbon, each of those groups being our chlorines. So then we would have to think in our brain, what would our shape for 4 things be? is this one, right? It's the tetrahedral geometry, where we make that X shape and we twist 90 degrees. So this is going to be tetrahedral molecular geometry. So that's our basic shapes. We also have some other shapes that are not quite as basic. So valence shell electron pair repulsion theory, the theory that we're using, that all the electron groups spread out as much as possible, will also cover things that have lone pairs. So if we have lone pairs in our molecule, in our compound, that's going to change our electron geometry and our molecular geometry. So our electron geometry is what's the shape of the electron groups. Electron groups are lone pairs, any number of bonds, single, double, or triple, they each count as one, and single electrons, like in odd electron species. Those all count as electron groups, and those determine the electron geometry. The molecular geometry is based on the arrangement of the atoms. So if you're thinking of, like if we were drawing this in, anywhere that we would have put our lone pairs for our electron geometry, just make that disappear. Don't change anything else, because it's still exerting a repulsive force. Just make it disappear or ignore it. And that will give you your molecular geometry. Alternatively, we can just memorize or refer to a table to figure out what our configuration is. But if you wanted to visually, like in your mind or making it with, a modeling kit, you would just make it disappear, leave all the atoms there, and that'll give you your molecular geometry. That's the actual shape of the molecule. So let's consider 4 electron groups with lone pairs. Ammonia is an example that falls into this category. So ammonia is NH3. Our nitrogen is in the middle. It's bonded to each of the 3 hydrogens, and we also have a lone pair on the nitrogen. Because we have a lone pair and 3 bonds, we have 4 electron groups. 4 groups means that we have tetrahedral geometry. So our electron geometry is tetrahedral. If we ignore this lone pair, because it's just electrons, it doesn't really take up space, then our shape is trigonal. We've got 3 points, but it's not flat, because that electron pair is exerting repulsion from the top, so it's pushing those other 3 groups away, and so it's not trigonal planar, it's now trigonal pyramidal. Questions? We can also have more lone pairs. 1 is not the only possibility. So let's look at 4 electron groups with 2 lone pairs on the next slide, I guess. We're first going to talk about bond angles. So lone pairs typically exert more repulsion than bonding pairs. So lone pairs exert more repulsion. There's a couple of ways that you can think about this. We can visualize it. The lone pairs kind of look like Toad from the Mario games. Kind of looks like Toad's head. It's a little bit more round and flat than if we've got a bonding electron pair. So that's one way we can think of it. It's a little bit more spread out. And because it's a little more spread out, it's going to be closer to where the electron groups would normally be, and so it's going to push them a little further away. So that's going to compress bond angles of the other groups. It's going to push them further away from this lone pair. Another way we can think of it is it's just 2 electrons, and it's not locked in between 2 nuclei. That's part of the reason that it spreads out. But we also don't have any nuclei with their positive force to like counteract the negative force. So you could maybe think of it that way as well. It's full strength 2 electrons instead of them kind of spending some time between the nuclei, alternating weekends or whatever. So in ideal tetrahedral geometry, we would have 109.5 degrees between all of our groups. Each of our pairs would have this 109.5 degrees bond angle. The actual molecular geometry, because we have this lone pair, these groups squeeze down. They get pushed away from the lone pair, and so the bond angle compresses. It's a slightly smaller bond angle. You would not need to know that it's 107 degrees, but you should be able to predict, because it's a lone pair on the other side, you should be able to predict that that bond angle is going to be slightly smaller. On the other hand, this bond angle between the lone pair and the hydrogens is going to be bigger than 109.5 degrees. So it'll be slightly larger because of that extra exerting force. It's making a little bit more space for itself. So this will be a slightly larger bond angle. It's not really a bond angle, but it would be a larger angle in that space. Now if we have 2 electron groups, or 2 lone pairs rather, in our 4 electron group molecule, that matches with what we see in water. So in water, we've got 4 electron groups, 2 single bonds, 2 lone pairs. So here's our lone pairs, here's our single bonds. So the electron geometry again is tetrahedral because we have 4 electron groups. And then poof, get rid of the lone pairs, pretend like they've disappeared, and now our molecular geometry is bent. And our bond angle is going to be even smaller because of 2 lone pairs pushing on the bond, or pushing the bonds away. And this molecular geometry we call bent. You can also get bent geometry if you have something that's got a central atom and 3 electron groups and one of them's a lone pair. This one, the electron geometry would be trigonal planar. And the molecular geometry would also be bent. So that's another way that you can get that bent geometry. So if we do like the YMCA Y pose and we get rid of one of our arms, then the bond angle or the shape that we make with the one arm and my feet, I'd get rid of the feet, but I'm not very good at floating yet. So we get a bent shape. Still, it's not linear, it's bent. That's one that you got to be careful with. All right, important piece of information on this slide is this ranking, the relative repulsion of electron groups. Our biggest repulsive interaction, because lone pairs exert the most repulsion, a lone pair, if they're right next to each other, that's generally really unfavorable. They're not going to enjoy being next to each other because they are bigger. They have more repulsive force. A lone pair bonding pair interaction is less repulsive, so those are more acceptable to have. And bonding pair, or bond-bond interactions are kind of like our least offensive interaction. So when we have the chance, we want to minimize repulsion. We always want to minimize repulsion. And so that means that we want to first prioritize getting rid of lone pair interactions if we have the opportunity to do so by changing up our geometry. Lone pair bonding pair interactions are better, and bonding pair interactions, those are the ones that we're okay having like 90-degree interactions. We'll see this show up when we start adding more groups on. So if you're confused now, just know that this is what we're going to be using some of this idea when we're making the next couple of not as basic shapes. Okay, what is the molecular geometry of a molecule whose central atom has 3 bonding groups and 1 lone pair? And that's all the groups. How many electron groups would we have for this molecule? Yeah, we would have 4 electron groups, and so that would give us what electron geometry? Yeah, it would be tetrahedral. If we get rid of one of those groups, then what would our molecular geometry be? Since one of them is a lone pair, that's why we're mentally erasing it. What would our molecular geometry be? Trigonal. Not planar. Pyramidal. Yeah, trigonal pyramid. Pyramid is how it's written here. Or tripi. So this would be a trigonal pyramid. Trigonal because there's 3 bonds. Pyramid because they're not flat. They're getting bent out of being flat. Right? This shape. If I get rid of I'll get rid of the backhand, and you can see that I've got the hand pointing towards you. You can even bend away from the hand. Right, the hand is not straight up in the air. It's kind of bent out of the plane. All right, jumping up to 5 electron groups. If we look at the Lewis structure for sulfur tetrafluoride, our electron geometry is bipyramidal. We've got the pyramid on top, we've got the pyramid on the bottom. The molecular geometry, though, is what we call seesaw. So one of the options that you could come up with for how to put this together, before we get to the molecular geometry, just looking at the electron geometry, you could put the lone pair in the axial position, one of the axial positions. The problem with putting it in the axial position is that you've got 90-degree interactions between the lone pair and the equatorial positions. And 90 degrees is our smallest angle that we typically see, and that's very unfavorable. So 3 90-degree lone pair bonding pair interactions is not good. If we put it on the equatorial position, then we only have 2 90-degree interactions. 2 is fewer than 3. And so it's more favorable for our lone pair to go in one of the equatorial positions. These 120-degree interactions don't even come close to the 90-degree interaction. So we're minimizing our 90-degree interactions between the lone pair and the bonding pair. And that results in this seesaw shape because we've got the one coming up and the one going back. So if you lay it flat along this axis here, then it sort of looks like a seesaw.
I was picturing it like upside down, like those are the legs.
Those could also be the legs. That also works. Yeah. That's probably better. either way, they would probably seesaw. So that's our molecular geometry for 5 electron groups with 4 bonds, or 4 bonding groups. We can also have 2 lone pairs. So adding another lone pair, still working in this 5 electron group electron geometry. So we still have our trigonal bipyramidal electron geometry, but 2 of them are lone pairs. And just like with 1 lone pair, we want to put them in the equatorial positions. When they're in the equatorial positions, that minimizes the 90-degree interactions or repulsions. And so we get this T-shaped geometry, but it's on its side. It's a sideways T-shaped. And again, this is to minimize our 90-degree lone pair bond interactions. The other thing that would happen if we put one of these lone pairs in an axial position is that we'd have a 90-degree interaction between the lone pairs, and that would be really, really bad. That's like the worst case scenario. Avoid at all costs. We can also have 3 lone pairs. If we have 3 lone pairs, the lone pairs go into the equatorial position, just like they did before. Again, to avoid those 90-degree interactions. And we end up with linear molecular geometry. And we should have a 180-degree bond angle because the lone pair forces will cancel out because they're applying equally to both sides in all directions. Any questions about our trigonal bipyramidal configurations? Okay. Who remembers what it's called when we have 6 electron groups? Octahedral, because it will have 8 sides. 6 groups, but 8 sides. So if we have octahedral, when we're octahedral, we have all 90-degree bond angles. So it doesn't matter where you put it, every single spot is the same. If we look here, right, we're going to have 90 degrees between these, and these. If we put it over on the side, it's still going to be 90 degrees between 4 groups. So it doesn't matter where we put it, at least for the first one, it doesn't matter where we put it. So we can put it anywhere. It's just a different orientation of mixing it up. And so what this gives us is square pyramidal position, or molecular geometry. Square because we've got 4 corners to our pyramid. So these are our 4 corners, and then the pinnacle or the point of our pyramid being in the other axial position. Just the way that we've drawn it. If we had another electron pair, where would be the best place to put our other electron pair? Knowing that we want to minimize interactions between electron pairs. How can we get our electron pair, our lone pair, as far away as possible from this other lone pair? We'd put it on the opposite side. So we can put, if we've got 2 lone pairs, we put them on opposite sides, they don't get along. Otherwise, we'll end up with 90 degree lone pair interactions. And what we get is square planar. So we've got 4 points. This is just the X shape. But like if I was being speared by a giant anything that had like lone pairs on it. So our molecular geometry is square planar. So our lone pairs end up across from each other. And this is all summarized in this table that's like 1.5 slides, sort of. So in the book, it should be table 11.1 or something like that. So you can figure out the number of electron groups on our central atom, find which entry matches the number that you counted up to, and then figure out how many lone pairs you have. 0, 1, 2, 3 in that same line, and then that'll tell you what your electron geometry is and your molecular geometry. It'll also give you approximate bond angles. Sometimes it'll be less than 90. For our trigonal bipyramidal shapes, it'll also tell you if it's equatorial or axial. And then there's some like picture examples. If you'd like to play around with making molecular models and you're not doing the retake, or if you just finished the retake early, we do have molecular modeling kits where you can they're colored foam balls, and you poke in a toothpick and then you add another foam ball to the other side. We have those if you'd like to play around with them. That was what we were normally going to do, scheduled to do for today. Okay, imagine we've got a molecule with 6 electron groups. It's confined to 2 dimensions, so it's flat, which gives it a hexagonal planar electron geometry. So it is flat like we see it here. It's not octahedral. If 2 of the 6 groups are lone pairs, where would be the best place to put them? Yeah, probably 1 and 4. So that they're on opposite sides. The definite worst place to put them would be 1 and 2, right next to each other. They definitely do not want to be right next to each other. If we put them at 1 and 3, then they would both be pushing on 2. And so then it's sort of like you've just got a person in the middle. And so they're still sort of kind of pushing directly on each other, just through 2. With them at 1 and 4, we can just squeeze down on these 2-3 interactions. Those bonds will just squeeze closer together. So that kind of acts as like a suspension or a little bit of a cushion between our lone pairs on 1 and 4. For their forces from 1 and 2 and 3 and 4. All right. Summary of valence shell electron pair repulsion theory. So our geometry, the shape of the molecule, is determined by the number of electron groups on the central atom. The number of electron groups we determine from the Lewis structure. So we have to draw a Lewis structure. We might be able to make a guess about what the Lewis structure could be without actually fully drawing it out and being robust about it. The safest way is to go through all of the steps of drawing the Lewis structure just to make sure you don't forget any electrons. And then each of the following counts as 1 electron group when we're counting them. Lone pairs, any of our bonds, single bond, double bond, triple bond, those all count as 1 electron group. And if we have a single electron, like in a free radical or an odd electron species, that also counts as 1 electron group. the geometry, the actual shape, the molecular geometry. No, that would be the electron geometry. The electron geometry is determined by the repulsions. So the way that they repel each other, and our goal is to minimize lone pair interactions. Whenever possible, try to not have lone pairs next to each other in the shape, or you could also just memorize what all the possible configurations are. Buy some 3x5 cards, write the name on one side, how many electron groups, how many lone pairs, and you can just memorize them that way. The bond angles can also vary. Multiple bonds are bulkier than single bonds. Lone pairs are also more repulsive, so we might end up having some squeezed bond angles if they're away from lone pairs. Which of these statements is always true according to VSEPR theory? Yeah, the correct answer here is D. The shape of a molecule is determined by the repulsions among all electron groups on the central atom, or interior atoms if we have more than one central atom. We won't get too deep into the weeds with interior atoms, but we will cover that a little bit. I think that's the next couple of slides. So the shape of the molecule is determined only by repulsions among bonding electron groups is not true, because we can also have lone pairs. Determined only among non-bonding electron groups is also not true, because we can have bonding electron groups. So those are both missing what the other one has. And the polarity of the bonds doesn't really determine the shape of the molecule at all. So it's A and B combined, which is D here. So if you want to predict molecular geometries, the starting place is drawing out the Lewis structure. So make sure that you can draw out Lewis structures. If you would like extra practice, I don't remember how much is on the Alex homework. If you'd like extra practice, the molecular models lab that we had previously scheduled for today, you still have it in your book. I believe I have the key and can share that with you if you would like to do the worksheet and then check your work. That would be good practice for predicting molecular geometries. So you'll draw the Lewis structure, determine the number of electron groups around the atom, determine the number of bonding groups and lone pairs, so breaking down the electron groups into two categories. And then you can either refer to table 11.1, that's this one, or with a physical model like marshmallows and toothpicks, or with just thinking about it, drawing it out, whatever you want to do, you can come up with the molecular geometry that way as well. Okay, one for you to try. Predict the molecular geometry and bond angle of ClNO. Okay. First step, Lewis structure. These are going to show up in the order that we see them. Chlorine on the outside, nitrogen in the middle, oxygen on the right. Generally, halogens, group 7, that chlorine's in, generally they like to form one bond and have 3 lone pairs. This is how they secure for themselves a formal charge of 0. They want to have 7 electrons on them. If they've got one bond, they still have their octet, but they have a count of 7. They get the 6 from these lone pairs, plus they get half of this bond, which gives them 7. Oxygen, on the other side, likes to form 2 bonds and have 2 lone pairs. That's the most common configuration that you'll see for oxygen. For the same reason, if we think about the formal charges, it's got 2 in each of these lone pairs for 4, plus half of the double bond, or some cases it'll be 2 single bonds to bring it up to a total of 6. It wants to have 6. That gives it a formal charge of 0. So typically halogens will have 1 bond. Things that are in the oxygen group will have 2 bonds. Things that are in the nitrogen group will have 3 bonds. And then you just fill in the rest of the octet electrons with lone pairs. If you did not do a Lewis structure, you might not have thought to put a lone pair on nitrogen, and you would end up with just 2 bonds. You would have gotten linear geometry. It's not linear, though. We've got 3 groups. What's our electron geometry for 3 groups? What's our trigonal planar. Trigonal because it's 3 groups. Planar because it's flat. So it really should be more like this, omitting some of the lone pairs. It should be like this around our nitrogen. What is the actual shape? If we ignore the lone pair, what is this shape? What's that molecular geometry? Bent. Okay, now bringing back the lone pair. Assuming no extra repulsive forces, what sort of angle should we get between these 3 groups? What would we expect? What would our ideal angle be if they were all the same? How many degrees are in a circle? 360. If we've got 3 groups, cut it 3 ways, 3 slices. We would have a 120-degree ideal bond angle. So that would be the angle between the chlorine and the oxygen. However, this is not an ideal situation. We have a lone pair. What does the lone pair do? Does it repel more, the same, or less than a bonding group? It repels more, and so that's going to cause this to squish down. It'll be less than 120 degrees actual. So less than 120 degrees because of the lone pair. Lone pairs repel more because they're a little bit more spread out. They're not locked between 2 nuclei. Question?
How off would I be if I put greater than 110 degrees?
You would probably be correct. It's probably more than 110 degrees. It's probably like 117 degrees. But since 120 is our ideal, we would want to frame it with that as our reference point. But you're in the right ballpark. Other questions? Okay, one more for you to try. Predict the molecular geometry of this, I3 minus. Okay, we want to predict the molecular geometry of I3 with a 1 minus charge. What's important about the 1 minus charge? Extra electron. So this negative means that we have an extra electron for our electron count. That is important. You could probably arrive at the same molecular geometry if you forgot that that's the case, but some other issues could arise. Okay, so to put this together, we need to start out with laying them out, and some of you might not be able to believe this. It's III. So dumb. And then we have to connect them with bonds, and we also need to know how many electrons do we have. We've got 3 times 7 electrons each, which would give us 21 electrons plus that 1 electron from that 1 negative charge. So we've got 22 electrons to place. We put 4 of them into bonds just to get it connected, just to start things off, so that it's an actual molecule, or ion in this case. And that's going to leave us with 18 electrons left. We can place those electrons on our outermost iodines. We can put 6 on each of these. So that would be 12 electrons to our terminal iodines, which means we have 6 electrons left. And we run into a potential issue, right? So our iodines on the outside, our terminal iodines, they've got 2, 4, 6, 8 electrons. They have their full octets. These iodines are happy. Our iodine on the middle does not have a full octet, and we have 6 electrons to place. So we could definitely put 2 lone pairs there, but we still have 2 electrons left. We already have single bonds. That's the minimum amount of sharing that we can do. Where can we put this last lone pair? If we've already got full octets, where can we put our last lone pair? It's also on the middle iodine. So because iodine is big, it's in row 5, it's big, it has access to d orbitals where it doesn't have electrons yet. And so it can use its extra d orbitals to go into an expanded octet. So we've got an expanded octet compound. This only works because iodine is big. If we tried to do the same thing with fluorine, fluorine is small. It does not have d orbitals because it's in row 2. And so we would not be able to make this compound with the negative charge. So it goes in there. We get an expanded octet, and we put a 1 minus charge on the outside. Question?
So I was thinking, like formal charges, like when I was trying to make this, where it's like, remember, like, I guess you want like more electronegative, or like you want the more negative formal charge on the outside if possible, right?
You want, so if you have an option of multiple places to put negative formal charges, you want it on the more electronegative atom. These are all the same electronegativity, so we would just put it on the middle one. And then this negative for our formal charges shows up because this iodine in the middle has a -1 formal charge. It's 7 minus 6 plus 1/2 of 4 equals -1. The iodines on the outsides all have formal charges. Both have formal charges of 0. So our overall is -1, which matches with our formal charge, which is perfect. All right, that's all just to get to the point of figuring out the molecular geometry. How many groups do we have in our central atom? We have 5 electron groups. Who remembers what that shape is? Yeah, it's trigonal bipyramidal. Trigonal bippy. Trigonal bipyramidal. Our number of bonding groups, we've got 2 bonds 3 lone pairs. If we referred back to table 11.1, we can look down to where it's 5 electron groups, 2 bonds, 3 lone pairs, and you should find that this gives us linear for our molecular geometry. So the way we've typically drawn it, we would have them actually all stacked up. And then in the equatorial positions would be the lone pairs. I don't know why I drew them that way. So this ends up being linear. If you want to represent molecular geometries on paper, you probably don't, because you probably don't want to represent molecular geometries at all. But if you did, if you were required to, this is how one of the ways that you can do it. So there's ways of drawing 3-dimensional bonds or representing things in a way that chemists understand are 3-dimensional. You might see this if you look at chemical formulas or chemical structures at some point. So the straight line means that it's a bond in the plane of the paper or in the plane of the board, whatever you're looking at. It's flat in the space that you're looking at. We also have these hashed wedges or hashed line. And we've got the solid wedge. These hashed lines are going away. So they're going behind whatever it is that you're looking at, going away from you. They can be at down and up angles. And then the solid wedges are coming out of the board towards you. You can also, instead of these lines, you might sometimes see it as an empty wedge or an unfilled wedge. That's typically what I did to represent molecular geometries, because I didn't like drawing all of the little lines and trying to get the spacing right so that it actually looks like a wedge. So you can also do that. The way that I remember these is that these are the hashed lines and these are the wedge lines, and wedges remind me of things that are wedge-shaped, like potato wedges or pizza, both of which are very yummy and tasty, and I would like to eat them. Right, so those are things that we want to put into our mouths, whether it's good for us or not. And then hash or hashed lines, keep that away from us. Hash being a...
Hash brown.
No, not hash browns. Hash being like there's a drug that's hash. Anyway, this would be how you would represent all these different shapes, or ways that you could represent all of these different shapes. It can get a lot more complicated than this. And you can also like rotate these in 3 dimensions. So there's a lot of different ways that you can draw these. This is just one representation. You won't be doing much of this, if any. We can also have larger molecules that have more than one interior atom. These are actually really common. And so for these, if we wanted to predict the shape, we can determine the geometry around each of the interior atoms. Typically, these are going to be easier. We're not going to see expanded octets, typically, which is great. So if we look at this molecule or this molecule, they're the same thing. We would look at our interior atoms. Our nitrogen here on the left, we've got 4 electron groups. Our carbon has 4 electron groups. Our other carbon has 3 electron groups. And our oxygen has 4 electron groups. So 4 for our nitrogen. One of them is a lone pair. And so this has trigonal pyramidal geometry. Our carbon here has 4 groups. They're all bonds. And so it's got tetrahedral geometry. Our right carbon has 3 groups, 3 bonds, so it's trigonal planar geometry. And the group on the right, our oxygen, has 2 bonds and 2 lone pairs. So it would be tetrahedral electron geometry, get rid of 2 of the groups, and it ends up being bent geometry. We could also do that for something like this. So predict the geometry around each interior atom in acetic acid and make a sketch of the molecule. So to start with something like this, we can look at how many things are bonded to each of them. So our carbon, this left carbon, has bonded to it. We'll draw it flat first, and then we'll arrange things appropriately. It's also bonded to this other carbon, which is double bonded to an oxygen, which is bonded to an oxygen, which is bonded to a hydrogen. And to fill out the octet for our oxygen, the oxygen also has 2 lone pairs. Lone pairs are not going to be shown generally in structures. So this would be our flat layout, not with the correct bond angles. So looking at our left carbon has 4 electron groups. It has 4 bonds. So its molecular geometry and its electron geometry are going to be the same. What is 4 groups? What's our name for that? Tetrahedral. So that's going to be tetrahedral geometry. Our middle carbon, or our right carbon, has 3 electron groups. They're all bonds, so they all take up space. So our electron and molecular geometries will be the same. And so this is going to be trigonal planar geometry. And then our oxygen, here on the right, has 4 electron groups, but only 2 bonds. So its electron geometry is tetrahedral. If you get rid of 2 of those groups, and then you've got bent geometry for the 2 remaining groups. The electron pairs, the lone pairs, are pushing away the other 2 groups, squishing them, making them bent. So our molecular geometry would be bent. And then to sketch the molecule, I'm going to start with the trigonal planar carbon. Trigonal planar is going to give us approximately 120-degree bond angles, so that would look something like this. On the right, we're going to have the oxygen. On the left, we're going to have the carbon. For the oxygen, we've got 3 possible options for where we can put our hydrogen. We've really got more. The easiest way to put this hydrogen is just up and to the right, so that in our tetrahedral electron geometry that I'm doing with my body right now, you do the X and you turn 90 degrees to the right. If our hands are both the lone pairs, one of them is coming towards you, one of them is going away from you, and then the bond with the carbon is in the plane, and the bond with the hydrogen is also in the plane. So this avoids having to draw any wedges or dashes, which is cool. And then on the other side with our other carbon, we have to draw in 3 hydrogens. So continuing the idea, we're going to draw one of the hydrogens up and to the left. So these are our 2 planar groups. They're in the plane of the board. And then we're going to have 1 hydrogen coming out to the front, 1 hydrogen going back. And these will both be something like this. This is still relatively simple in terms of like all of the molecules that exist everywhere. Questions about putting together any of this? Figuring out the geometries, drawing out the sketch. This isn't the only way to draw it. There's other ways you could draw it. Okay. What is the molecular geometry of the nitrogen in CH3NH2? Note that the elements are not necessarily in the order that they're bonded. All right, so this molecule is going to look something like this. Nitrogen gets a lone pair. This gives each of our hydrogens one bond like they like. Our carbon gets 4 bonds. Our nitrogen gets 3 bonds and a lone pair. It's all normal stuff. What is our molecular geometry around the nitrogen? It's got 4 electron groups. It's got 3 bonds. 4 electron groups is going to give it tetrahedral electron geometry. If you take away one of those, how many groups are left? 3. Our prefix for 3 is tri, so it's going to be one of our trigonals. Is it going to be flat, or is it going to not be flat? Is it going to be a pyramid? It is going to be trigonal pyramidal because of this lone pair. Okay, we will get a little bit into polarity. If we have a diatomic molecule, the entire molecule, the whole thing, all 2 parts, is going to be polar if the bond is polar. So if we have a difference in electronegativity from about 0.4 to 2, we've talked about electronegativity before, right? I think we have. If we've got a polar bond, it's going to be a polar molecule. There's nothing to offset the partial negative, partial positive, not in that order, of these charges. So for diatomic molecules, it's simple. If there's a polar bond, it's a polar molecule. If we've got a polyatomic molecule, the polarity depends on the geometry. So the dipole moments, the polarity of the bond, can be canceled out if we've got a bunch of these going in the correct directions and having the correct strength. We will not be looking at versions where it's like super, super weird. One example of these canceling out is if we look at CO2. CO2 contains 2 polar CO bonds. I believe the difference in electronegativity here is 1.0. Carbons 2.5, oxygens 3.5. However, the molecule is linear, and so these arrows are going in opposite directions, and it's the same polarity, it's the same bond strength, difference in electronegativity, so they completely cancel each other out. And so this is actually non-polar because those arrows cancel each other out. So we've got 2 considerations that we're going to be thinking about when we're figuring out if things are polar. The first is the direction. The direction of the arrow is pointing towards the more electronegative atom, and there's also this little plus sign that we put on the more positive side, the less electronegative atom. So we're pointing towards the negative side. There's also the magnitude, which is proportional to the electronegativity difference. Proportional to, we're not going to like put hard and fast numbers to it. We can just think about it in terms of difference in electronegativity. These are both going to be arrow size 1, whatever that means. If we had one that was 0.5, we'd draw it as half the length of the arrow. I'm talking about the more complicated details. I don't think we're going to use them very much because it gets a little confusing. If we've got something like water, water contains two polar OH bonds, 3.5 minus 2.1. We've got a delta En of 1.4. It's definitely polar. But because the shape is bent, these arrows are both sort of adding up. They're not completely canceling each other out because they're not pointing in opposite directions. They're both pointing a little bit up the way that we've drawn it. The left and the right components will cancel each other out, but the up components actually add. So this arrow that's drawn here, not to scale, this arrow shows our overall polarity of the molecule. So we've got a partial negative up here on the oxygen side, since it's the more electronegative atom, and then we've got partial positive just generally down in the hydrogen side of water molecules. For figuring out polarity from our molecular shapes, you need to draw a Lewis structure. So hopefully we'll be good at drawing Lewis structures, and determine the molecular geometry, the actual shape of the atoms after you figured out the electron geometry. Then you need to determine if the molecule contains polar bonds. It must have polar bonds to be polar. So if you do your electronegativity calculations with your yellow sheet or with values that are provided and there's no polar bonds, then you can just stop there and say it's not polar because it doesn't have sufficient bond strength difference in electronegativity. If it does have polar bonds, then you can draw in the polar bonds with vectors. Yay, vectors. These are going to be pointing towards the more electronegative atom, and their length should be proportional to the change or the difference in electronegativity. The fish-looking thing here meaning proportional to. It's whatever scale that you choose to draw it at, it's all kind of rough. And then you'll determine if those polar bonds add together to form a net dipole moment, an overall arrow with the way that we've been doing it. If those vectors, if the arrows cancel out, if they sum to 0 or close to 0, then it's going to be nonpolar. If we do have an overall arrow, they're not canceled out, then the molecule would be polar. I'm going to skip that. This is what vector addition would look like if we were doing vector addition, if you have to use it, if you feel like using it, learning it. So if we've got one dimension, vectors are all going to lie on the same line. So we can assign a direction as positive. Typically that's probably going to be to the right is going to be positive, to the left would be negative. If we've got two arrows to the right of values of +5 each, then together they would add up to +10. If we've got 10 to the right and 5 to the left, you subtract the 5 from the 10 and you get an overall of +5. If they're +5 and -5, right, 5 to the right, 5 to the left, think of them as maybe pulling forces like we're doing tug of war. 5 to the right, 5 to the left, nobody's going anywhere, right? Those are going to be canceling each other out. And in one dimension, I think relatively easy. You're just adding together what all the numbers are. It gets more complicated when we add more dimensions. So if you have more dimensions, if you have 2 dimensions, I would recommend drawing it like a graph, like an XY graph. So you've got the up component, the Y component, the X component in the left, right. So we're going to split vectors to X and Y parts. So for example, if we have something like this. And we've got some electronegative forces. And I'm going to make this B instead of X so that it maybe makes sense in some universe. We want to split up all these arrows into their X and Y components, just vertical and horizontal, so that we can assess them. So I'm going to break these diagonal arrows into left-right components, and we'll also take their vertical components. And we're going to use those arrows instead of the diagonal arrows. So we can see the left arrow, the right arrow, those are about the same size, they're pointing in opposite directions. Those cancel each other out. The vertical component of these green arrows adds up. So we would just stack two of them, and then we look at this stacked addition of these green arrows and compare it to the red arrow. And how do those sizes match up? They look about the same to me. About the same. So those would probably cancel. It gets even hairier if we work in 3 dimensions. This is the basics of how to do vector addition. It's really beyond the scope of this class to work with vectors, I think, but you should know how to do it. If you've got 3 dimensions, then you get to break it down into 3 dimensions, so X, Y, and Z axes. However, we also have a shortcut, and this is why I'm rushing through vectors. I don't think the vectors is terribly important, and we can generally just use this shortcut. This is Mrs. K's shortcut to molecular polarity, or as I like to refer to it, the nonpolar express. It's our fast track for finding out if something's nonpolar. We have 2 rules for our nonpolar express. A molecule will be nonpolar, that's why it's the nonpolar express, if both of these conditions are true. If one, we have no lone pairs on the central atom, that means we're going to have linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral geometry. Those are our 5 options. And all of the atoms bonded to the central atom are the same or have the same electronegativity. This will mean that the arrows are exactly the same size, and because we have no lone pairs on the central atom, they'll be perfectly spaced out so that they all cancel out. This allows us to bypass thinking about vectors, even vector from Despicable Me. We don't even have to think about him. So if both of these conditions are true, then the molecule is nonpolar. If either is false, and there are polar bonds, because we have to have polar bonds, it's probably polar. And by probably, that's like, I would guess 99% of the time, at least in this class. 99% of the time, it's going to be polar if it doesn't meet this nonpolar express. So this is what I recommend. I think this is a lot easier than doing vector addition. If you feel comfortable doing vector addition and scaling your length of your arrows proportionally to the difference in electronegativity, you're welcome to do that. That's the more robust way to do it. The nonpolar express, I think, is a great alternative and requires significantly less brain power. So this would just be, you'd memorize these 2 parts, and then boom, you've got molecular polarity solved, essentially. Question?
What about the trigonal bipyramidal molecular geometry? It seems like the angles are like, that
trigonal bipyramidal, you'll have axial, so you'll have up and down. If those are the same, right, those are going to cancel out.
Oh, okay.
And then the other ones is trigonal planar, and those will cancel out. One caveat for when this can be not true, for the no lone pairs part, if we have a linear geometry, this works perfectly for Chem 20. There's a couple of exceptions for our class. So if it's linear with lone pairs, if it's linear from trigonal bipyramidal, then those arrows will also cancel out. So we can't just use the nonpolar express. If it's square planar from octahedral, the same idea. Those could also cancel each other out. So that's where we've got lone pairs in the up and down positions. And we would have, that's a terrible wedge. We'd have groups around the perimeter. We'll just make those all X's. These would also both be nonpolar.